So, good morning. This is a lecture on computer control. And today we are going to start studying basic notions about models. Okay? Models, as I said several times before, are essential. There is no engineering without models. You must rely on a model to do your design and to test your design. And you use models to do the design and also to validate your design. When you design a controller, then you have to test it. And the first tests are in simulation. The models that I'm going to speak about are more appropriate for design. Usually, models that used for validation are more complicated, physically based models, sometimes even hybrid models. We are going to concentrate on models that you can use for design. Now, there is a danger in this lecture, because this lecture, I think it's very boring. I'm bored presenting this lecture, and I imagine that you will be bored too, but it's quite important. Because if you must know the structure of these models. It's very simple, but there are a number of details. And this will be used along the course. So this is a kind of basic brick that we have to put in the construction of the knowledge of this course. Okay. So the first thing is we are going to consider linear time invariant systems in discrete time. Okay. Discrete time you know already. So the signals are made of a sequence of numbers, and you have an input sequence and an output sequence, and your system transforms the input signal into the output signal. You had before a course on signals and systems, so this is nothing new to you. And furthermore, apart from being in discrete time, we are going to consider time invariant systems. Okay? What is a time invariant system? Is a system that if you do an experiment now, so you apply some stimulus to your system and you get some results, okay? And you do it now at 9:38 in the morning. Now, if the system is time invariant and you apply your stimulus, say at 2:00 past noon, then you will get the same shape of the result, but shifted by the time between present time and 2:00 in the afternoon. Okay, so it's not exactly the same thing. It's the same thing, but shifted, as the same shape but shifted. So in mathematical terms, if you apply a sequence, a function u of k, k generic, and you get an output y1 with k generic. This is the definition. Okay, let me see if I have the, okay, time invariance here. If you apply a sequence u of k and you get an output y of k, now if you shift your input, then you get an output which is shifted. And if you keep all the initial conditions and so on, you get an output which is shifted by the same amount of time. Okay, that's the definition of time invariance. Now, linearity, it's the situation in which the superposition principle holds. So this means that if you apply a sequence u1 and you get a response y1, now you apply another sequence u2 and you get another output y2. The system is linear if you apply a linear combination of both inputs u1 and u2, you get a linear combination with the same coefficients of the responses to U1 and U2, so Y1 and Y2. Okay, that's the definition of linearity. Remember that the system can be linear without being time invariant. It can be time invariant without being linear. So we are going to consider that these two properties hold, and you have studied an important result, which is for linear time invariant systems. If you know the response to one function of the input, then you can know the response to all other functions, provided that you don't apply something which is trivial, such as everything is zero. Okay? So, in particular, you can characterize linear time invariant systems by the impulse response. You study that in the basic course on systems, signals in systems, or you can use the transfer function. Okay? We are going to review these things. So if you lose linearity or if you lose time invariance, then things become much more complicated. You can say, well, systems in true life are not time invariant. I mean, look at me. I'm quite different from what I was 10 years ago or 20 years ago. So I'm changing. No? When time passes, systems tend to wear desgastam-se, os sistemas desgastam-se, and they change their behavior. But for limited periods of time, many systems of technical interest can be considered to be time invariant. Now, for linearity, many examples are nonlinear, but you can use linear system models as approximations. For instance, if you work, say, suppose that you have a boiler, okay? So you are burning some fuel, and you get some rate of production of steam. Okay. Now, if you increase a little bit the rate of burning of fuel, say you were burning 10 tons per hour, and you start burning 10.5 tons per hour, then the steam that you are producing is a little bit also increased. And you can relate the increments in the input with the increments in the output with respect to the baseline, to the equilibrium point, by a linear model. Okay? In many cases, you can your problem is just a regulation one. So you want to keep your variables still. Okay, that's in classical production theory. Now you can say, well, but I can have a drone or a mobile robot, or even a robot that does not change, it's fixed, but it's a robot. And this is a strongly nonlinear system. Okay. Even in that case, you can identify linear systems around different possible equilibrium or possible operating conditions, and then patching together, that is to say, making an interpolation of the nonlinear system with linear ones. So linear systems are essential tool to understand and to design, to understand the world that is around us, in engineering terms, I mean, and not only that, and also for design. Even when you enter the world of nonlinear systems. So it's quite important that we have clear ideas about this. Okay, so let's concentrate on linear time invariant systems. The superposition holds. This property of time invariance also holds, okay? So in particular, we know that it's possible to prove. The proof is not difficult, but I'm not going to do it because you have studied that before. You can characterize it by the impulse response, for instance. Now, in discrete time, how can I write models for linear time invariant systems? One possibility is to write difference equations, such as I wrote here. Now, this slide is an example where the best intentions create the terrible results, because I wanted to explain things so much that I guess that this is hard to understand. But let's see what we have. We have Y is the output of the system, okay? And U is the input. And what we have here is a relationship. K is discrete time, and then is a constant. So imagine that n is 1 or 2 or whatever. It's an integer which is constant. So what you are saying is that you are relating the output at time k, generic k, time k plus 2, with the previous samples of the output and with the previous samples of the input. I say previous because if m is smaller than n, then this happened before y of k plus n. Okay? So this is a difference equation. At least some of you, if not all of you, have studied difference equations. So let's, sometimes we know, oh, well, I studied that, so I need not to pay much attention. But don't make that mistake, because we are going to learn how to write these difference equations in standard forms. You can write difference equations in many different forms. And we are going to write difference equations in 2 standard forms that will be useful later to study stability and to do design. Okay, so let's explain this a little bit better. What is the idea here? You start with some initial conditions, and your initial conditions must be n. N, remember, is the maximum delay or advance of y, okay? So if you look at here, you are expressing y of k plus n as a linear combination of these terms, of the previous values of y, okay, plus the past samples of u. So you can write y of k plus n equals to minus this stuff plus this stuff. And so you need to know the values between y of k and y of k plus n minus 1. This is n because this is 0, and then you have 1 up to n minus 1. So 1 plus n minus 1, that's n terms. You have n terms here. And you have m plus 1 terms here. Okay? So you need to know the first values of y, the first n values of y, to start to compute y of k plus n, and then you iterate. Let's see an example. Okay, so in this case, n is just 1. Okay, so you are expressing y of k plus 1 as a function of the previous y and u. Okay, m is 0, n is 1, and you must know the initial condition, because if you know the input sequence and you know the initial condition, then you go on iterating and you compute y of 1, okay, y of 1, and then from y of 1 you compute y of 2, and so on, okay? So difference equations are a kind of iteration. It's very simple. I mean, the theory is very simple. Now, we have seen already this. If you apply a constant u, is there a value, an initial condition for y such that y is kept constant at that value? It's very simple. You just force that all the values of y are equal to that constant value y bar. So this becomes y bar, yk plus 1, I assume it's y bar, yk is y bar. So I get an algebraic equation in y bar that I can solve. In this case, it was 2, but it can be anything else. So that's the notion of equilibrium. If you apply a constant input, what is the output such that if you start at that value of the output, the output becomes constant. That's the equilibrium. Now, here are the two standard ways of writing the difference equations for linear time invariant systems. One is with forward shifts, and the other is with backward shifts. So on the top, these two lines is what I just wrote before, okay? So you do a linear combination between y of k up to y of k minus n, okay? And you are saying that y of k plus n is dependent on the other terms. Now, you can make that dependency explicit by making a backward shift, fazem deslocamento para trás of n steps. So you do a backward shift of n steps, where you had y of k plus 1, now you have k, y of k. Where you had y of k plus n minus 1, now you shift n, so you have k minus 1, and so on, okay? And the same thing for u. So here, you have now yk expressed in the past values and u in the past values also. And what happens? The first one is better to study things like stability. And the second one is better to do designs, for instance, design of predictors or even controllers. Why? Because here, this is a kind of prediction. See, this is a kind of prediction. You are predicting y of k as the previous values. Now, let's see an example. Suppose that you have this difference equation. Okay, here n is 2, m is 1. You have u of k plus 1, you have y of k plus 2. Now, you can delay everything by 2 steps and you get y of k, then plus a1, y of k plus 1 minus 2, which is y of k minus 1, and so on. So you delay all the signals by 2 steps. So these are the two standard forms for the second order example. Now, remember that I could have been a bad boy, and I could have written y of k plus 5 plus 7, for instance, y of k plus 7, then plus a1 y of k plus 6 plus a2 y of k plus 5 equals to u of k plus 6. Okay, that is valid. But you write things in such a way that you start with y of k and you end with y of k plus something. Okay, that's a standard forward shift. And then in the backward shift, you start with y of k and you go backwards. Okay, so this is something that is very simple, but it's important that you have clear ideas about it. And the only trick is shifting the time. Okay, shifting the time. Now, Suppose that in this system, I apply the sequence. And do I have an instantaneous action of the input U on the output? What do you think? Or does it take some time? And if it takes some time, in this case, what is the time that it takes?
O tempo é 2, delay.
You say that the delay is 2. Why? Por que diz que o atraso é 2?
Está escrito no PowerPoint.
Oh, but what is written here is that from passing here to here, I'm delaying the time by 2 steps. I'm not saying that the process delays 2. Sometimes I write mistakes in my slides, but this one is correct. It's not. You say?
1.
Why is it 1?
Olhando para a equação.
Okay. What do you see by looking at the equation? Marcelo, you were saying something.
I think that we should look at our input and the output that is further away. For example, in this case, we have epsilon k minus 2, and we have u, which is our input, k minus 1, and they are apart 1 time unit. So it's our delay.
So
between our input and our output.
That's the correct way of thinking. Imagine that you are at time k, and you say, does uk affect yk? No, it does not appear. Now you ask, does u of k minus 1 affects yk? Yes, it affects, because if you change u of k minus 1, it depends. It affects yk, so the delay is 1. Okay. If I had here u of k, the delay would be 0. If I had here the most advanced value for u would be u of k minus, say, 5, the delay would be 5. Okay. Let's go back to the previous system. In general, what is the delay of this system where you have n advances in y and m advances in u?
N menos m.
N minus m, okay? Because yk is not affected by all the u's between uk and uk minus n minus m minus 1. So the first one that affects yk is u k minus n minus m. So the difference of these degrees, because this is a kind of degree, okay, this the largest shifts in u and y, gives you the delay. Okay. Now, in discrete time, later we are going to define the Z transform and the transfer function and so on. And n is the number of poles, and m will be the number of zeros. And the delay is nothing more than the difference between the number of poles and zeros. Okay? Which is quite nice in discrete time. This does not happen in continuous time. So can you give me, is this system called a condition for the system to be causal? You know what is causality?
The delay must be positive.
The delay be positive. The causality means that first you drink the beer, then you get drunk. Okay, you don't get drunk before drinking the beer. That's causality. Okay, so the delay between the input, the cause, and the output, the effect, must be positive. Now, in which situation do we have an instantaneous? Tell me a condition so that we have an instantaneous action of the input in the output. digam uma condição para que haja uma ação instantânea da entrada na saída. So you change the input and immediately the output changes.
O delay tem de ser igual a zero.
So n must be equal to m. Okay, the delay must be 0. If n is equal to m, then you have u of k minus u of k minus n is equal to m, so this is 0. So you have u of k. When u of k changes, y of k changes. So if n equal to m, then you have a 0 delay, so there is an instantaneous action. Now, tell me a condition such that the system is non-causal, that is to say, the system reacts to inputs that will appear in the future.
N bigger than m.
M bigger than n. Okay, if m is bigger than n, this term becomes negative, minus becomes positive. So u of k plus something is affecting yk. Yk is depending on future values of u. Okay. So for causality, well, you could place here n bigger or equal to m. In general, it's very rare to find systems with instantaneous response because the system has some inertia. Okay, so you apply some stimulus, and the system takes a little bit to answer, to respond to that. So in many cases, we are going to have n strictly bigger than m. Of course, n equal to m is causal also, but we won't consider this. Okay? So causality is related to the relation between the number of poles and zeros, something that I have not yet defined, but we can anticipate a little. Okay. And we have this notion of delay, which is nothing more than the difference of n and m. Okay. In many cases, I'm going to take as delay 1. And I say this is without loss of generality. Suppose that you have a system that has delay 2, but I assume it's delay 1. So what is happening? Suppose that n minus m, okay? Suppose that I say, well, n minus m is nominally 1, but the system has delay 2. So how can I save the situation in terms of the model? It's very simple. I just have the leading b is 0, okay? Because the one delay u is not affecting the output, so this time is not there. So I say it's 1, but this time is 0. Okay. This is a trick that you use to have more generality in your control algorithms. Then you must be careful so that everything mathematically goes well. There is no divisions by 0 or something. Okay. Sometimes you have to know exactly, in some design methods, you have to know exactly the delay. In some other methods, you don't have to know the delay. So of course, the methods for which you don't have to know the delay are better because it's one less thing that you don't have to specify than the ones for which you must know exactly the delay. And there are systems in which the delay is changing. Can you think of a system in which the delay is changing? May change? Suppose that the action depends on a fluid passing on a pipe. Okay? If you change the flow rate, se mudarem o caudal do líquido que passa, you are changing the delay because your action depends on some fluid passing on a long pipe, okay? And the faster it passes, the smallest is the delay, okay? And all the time you are in industry, you find situations like this where you have long pipes, and this imposes some delay, and sometimes the flow is not constant. So you have, now you have one delay, later you will have a different delay. Okay? These systems are not time invariant, you should be careful, but in certain periods of time, you can assume that they are time invariant with a given delay, and then you have another system and so on. Okay. Now, let's review the Z-transform. Have you studied the Z-transform?
Yes.
Can you? Yes, you have studied the Z-transform in signals in systems, wasn't it?
No, it's in PDS.
Oh, okay, but not all of you had PDS, wasn't it?
I guess not, because it's a master's class in the second semester only.
Okay. So let's review some basic facts about the Z-transform. Okay. Now, I usually tell a joke, which is this: suppose that you were in Roman times and you wanted to multiply two numbers using Roman notation, and it was a nightmare. I mean, I guess that the Romans could not multiply numbers because their representation of numbers was very bad. Okay, but then they came the Arabs, and the Arabs brought with them. They did not invent it, but brought with them a different representation of numbers. Actually, this representation was invented in India, but they were brought to Europe by the Arabs. And with this representation, which is the representation, the decimal representation that you know, when you write 1023, you write 1023. Okay, the Romans did not have a zero, neither this positional number, and it's very easy to multiply numbers. Okay, so if you were a Roman kid and you were at school, okay, and they asked you to multiply two numbers, you would be in trouble. But then if you had some Arab friend, you can ask him to transform the Roman number into an Arabic number, where it's very easy to multiply things. So you do a transformation of the number representation. You do a transform of the number representation. And in the new representation, the Arab representation, it's very easy to multiply numbers. So now what all you have to do is to multiply the Arabic numbers and then invert the transformation to get the Roman representation of numbers. Okay? So instead of doing a task which is very difficult, which is multiplying directly the numbers in Roman representation, you do first a transform that makes the problem much easier. You solve the problem in this easier representation, and then you apply the inverse transform. Okay? So the idea of transforms is the same. And you apply this to solving difference equations, the Z-transform. It's all of you have studied the Laplace transform. So the Z-transform is the counterpart of the Laplace transform for discrete time sequences. Okay, so suppose that you have a function of discrete time k is 0, 1, 2, 3, etc. Okay, we should be careful because if you look at the Z-transform presented by a guy from control like me, k starts at 0. If a professor is from the signal processing community, k starts at minus infinity. So minus infinity plus 1, etc. minus 1, minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay? But for people that work in control, I mean, systems start at one point. So we have the so-called one-sided Laplace transform. That's what we are going to consider. And this is a difference with respect to what you have learned in PDS. and I have big discussions with Professor Jorge Salvador. You know, for how long do I know Professor Jorge Salvador? We were friends since we were 16, okay? And already with 16, we had the idea of discussing things in science. You would laugh what we were saying about science and mathematics and so on. But that's another story. But still now I have a lot of discussions with him because, I mean, for me, you have a switch on your system, you make it on and you have an initial condition and you start from there. You don't come from minus infinity. But the guys from signal processing like that. Okay. So to this sequence of numbers, f of 0, f of 1, f of 2, you apply a function, you map this function of discrete time into a function of a complex variable that I call z. So z is a complex number, okay? And the definition of f of z, which is the z transform of f of k, capital F of z, is the z transform of the function f of k, is this one. So you have this series, is a summation between 0 and infinity of f of k, z of minus k. So in PDS, you had summation between minus infinity up to infinity. Okay, but let's forget about it. Okay, so let's give some examples. Two examples that are quite important in what follows. So suppose that your f of k is just 1, it's a constant function. Okay, that's our notion of step. And I want to compute the f of z, so I use the definition. Okay. Now, let me tell you one thing. To solve a problem, one important thing is to use the definition. I mean, suppose that I ask you, is Kibbles green? What is the first thing that you have to know? Se eu vos perguntar, o Kibbles é verde, qual é a primeira coisa que tem que saber?
O que é ser verde?
Desculpa?
O que é ser verde?
Bom, vamos admitir que sabemos verde, mas há uma outra coisa mais básica. Qual é?
Quem é o Skabelze?
O que é o Skabelze? Okay? So we need to know the definition of Skabelze. Okay? And only if you know the definition of what is Skabelze, you can decide whether it's green or not. Okay? So if I ask you to compute the Z transform of a sequence, the first thing that you know is what is the Z transform? That's the definition. You see, this is a way of thinking which you can apply in many instances, not only solving this particular problem. Always think about the definition. Many definitions, not all, give you a way of constructing the response to problems. Okay? So, I also have to remember the fact that if I have a summation of powers of basis R, if the modulus of R is smaller than 1, R can be a complex number, then this is 1 divided by 1 minus R. This is something that you prove in elementary mathematics. Okay, so let's use the definition of Z transform in this formula to compute the Z transform of a sequence which is always 1. So I use the definition. Now f is 1, so nothing appears here. So the summation of z minus k, now I can apply this formula. Z minus k is the inverse of z up to k, okay? Which is, I can use this formula with r equal to 1 divided by z. So the formula gives me this, provided that 1 divided by z is smaller than 1, okay? This is related with the so-called convergence region of the Z transform, which has an important interpretation in terms of causality and so on. Okay, so you can write the Z transform of the sequence, the time sequence 1, as being z divided by z minus 1. Okay? Let's see another example. Suppose that you would say an exponential, but actually it's a power, because e is the number e, 2.718 and so on. And a is a constant, and h is a constant, and then you have k, the discrete time. So this is the same as e of ah up to k. So it's the power k of the exponential of ah. The exponential of ah is a number. Okay? So I write it in this way because it's useful in terms of what we will be doing later. But this is nothing more than a power of k of a number, which is the exponential of ah. Now, again, we use the definition, and we use the same formula for the summation of the geometrical series. Okay, so use the definition. So replace the general value of f of k by our sequence. And now we use basic properties of powers. And I can write this product as the power k of the product of the bases. Okay. Now I use the sum of the geometric series. So I have some r up to k. So it's 1 minus r. Okay. Which I can also write by multiplying above and below by z in this way. So the z transform of the exponential of ahk is nothing more than z divided by z minus the exponential of ah. Okay. Then I could go on and I could write a table. I could write a table. Here you have several examples. For instance, if you have the impulse in discrete time is very simple because it's a sequence which is 1 for k equal to 0 and then 0 elsewhere. Okay, and the z transform is just 1. You can prove it very easily from the definition. If f is just 1, we have just proved it, z divided by z minus 1 and so on. Okay, you can compute. Some of these expressions give you some algebra, some other expressions you can obtain with properties from the z transform and from some other z transforms. So the z transform has a number of properties. The first property is linearity. If you have two sequences, f of k and g of k, and you do a linear combination where alpha and beta are coefficients, the z transform of this linear combination is the linear combination of the individual z transforms. Now we have time shifts, and these are very important, very much important. So the z, if you let me introduce some notation that I have not yet defined. What's the meaning of q minus n? It's f of k minus n. So I say that f of k minus n is f of k shifted backwards n times. So I say it's like applying an operator that shifts backwards f. Okay, and if I shift backwards, if I know f of z and I shift backwards f of k, then the z transform of the shifted sequence is z minus 1 times the z transform of the original f of k. Okay? If I do the shift forward, then I have to consider the initial conditions. This appears because I'm considering the unilateral z transform. The bilateral z transform, you don't have this term here. Okay? If the initial conditions are 0, so if the initial values of f are 0, then this term is not there, and you just multiply f of z by z up to n to obtain the z transform of f of k plus n, k up to n. This is shifting forward f of k. Okay? Two examples I give here. Otherwise, I must consider the initial conditions. Okay. Then we have one thing which is the final value theorem that says that when you compute the limit of f of k when k grows unbound, it's given by this formula here. It's a limit with z going to 1 of this quantity. You have a similar result for the Laplace transform. And then an important result. Suppose that you have the convolution of two sequences, which is defined by this summation. Looks awful, isn't it? Okay. Fortunately, we're not going to use it very much, but conceptually, it's quite important. And if you apply the z-transform to the convolution, you get the product of f of z times g of z. So you get the product of the z-transforms of the functions f of k and g of k. Okay? Exactly as in the Laplace transform. Now, we can apply these properties to solve difference equations. So suppose what are we going to do? We are going to apply that strategy of multiplying Roman numbers that I just said. So suppose that you have a difference equation. You don't know how to solve it. You want to get a solution, but you don't know how to pass from the difference equation to the solution of the difference equation. So what you do is you apply the z-transform. And when you apply the z-transform, you will get an algebraic equation that you can easily solve because you know a lot of algebra. I hope so. And if you solve the algebraic equation, that's an easy task. You get the solution of the algebraic equation for the z-transform. And then what you do is you apply the inverse z-transform. Okay? Now, to apply the z-transform and the inverse z-transform, you use the tables that you have compiled for the z-transforms. So by going this way around, you solve the difficult problem of solving the difference equation. Let's apply this to solving a first order equation where a and b are constants, and we have a zero initial condition. So we have our difference equation, and we apply the z-transform. So with zero initial condition. If you apply the z-transform to y of k plus 1, you get zy of z, and then the correction term for the initial condition. Okay, I was saying that this was 0, so you could not have written it. Now you have by linearity, you have the sum of two terms. You know that a linear combination of y and u, so the z-transform of this linear combination is the linear combination of the corresponding z-transforms. Now, what you have here is an equation in terms of y, because you have y of z here, y of z here, z is z. Okay, y of 0 is a constant that you know, and u of z is something that you know, because you know u of k, so you can compute u of z. Okay, so you solve this with respect to y of z, and you get the sum of two terms. One term depends on the input, that's a forced regime, and the other term depends on the initial condition. Okay, that's a transient regime. Okay, now if the initial condition is 0, this transient is not there, and all you get is this stuff here. Now, if you know u, imagine, for instance, that u of k is a constant equal to 1, then you know the u of z. It's z divided by z minus 1. You can look at the table. Okay? Now, the big trick is to say what is the time function whose z-transform is this one. So you use a technique known as simple fraction decomposition. So we are going, you have two terms of the form z minus a and z minus 1 in the denominator. So you can split this fraction into two fractions using something that you have studied, and I'm not going to lose time on this stuff, known as simple fraction decomposition. If you want, the problem is to find the coefficient here and the coefficient here such that this sum is equal to that. You can use the residuals theorem, or you can just add these two functions, which is something that I assume that you know. Okay. Now you can write this in this other formula. Okay, and you recognize that z divided by z minus 1 is 1. And this term here divided by z is, you have the division by z. The division by z is a delay. Okay, so it does not affect this term because this is always 1. So if it is always 1, and if you delay it, you still get 1. And here you get the z transform of a up to k. Okay, that's the second example. Where is it? If you repeat this example as a up to k instead of this formula here, you get z divided by z minus e up to k. Here, okay? So you get your expression for yk. Okay? Now, in this course, I'm not going to insist much on solving difference equations, but it's important that you understand this this procedure. And what I really want to do with the z transform is to introduce the notion of discrete transfer function. So suppose that you have a linear time invariant system with input u and output y, and it's described by this difference equation. Now you apply the z transform with 0 initial conditions. That's important that you apply with 0 initial conditions. So where you have y of k plus n, you will get y of z times z up to n, and so on. So here you are going to have y of z multiplied by z up to n plus a1 z up to n minus 1, and so on. And then you the same thing for u, and you solve it with respect to y, and you get y of z equals to this coefficient of polynomials times uz, or yz divided by uz is equal to that stuff. And this is the transfer function. Okay, so if you want a definition, the discrete time transfer function is the quotient of the z transforms of the output and the input with 0 initial conditions. Don't forget the story of the 0 initial conditions. Same thing as you have studied in continuous time with the Laplace transform. Now, okay, I have already spoken about the forward shift operator. I call it Q. So think of this as an operator, not as a variable. And what does this operator do? It picks up your sequence x of k and generates a different sequence which is advanced by 1 unit. So that's why we call it the forward shift operator. Okay? Now, suppose that you take again the difference equation of general order n. And you can rewrite this in a different way. Now I'm going to write things as q were a variable. It is an operator, but let's forget for a moment it's an operator. Let's think it's just one complex number. Okay, so you write y of k plus n as q up to n yk, and so on for the other powers. And you can write a difference equation in this term. Okay, you can say, well, this is the Z transform. Okay, this is nothing more than the discrete transfer function, but there is a difference because here you have the Z transform, you have the Z variable, which is a complex variable, and here you have an operator. In continuous time, you have S, which is a complex variable, and you have DDT, which is a difference operator. Okay? Actually, you don't do this in continuous time because the derivative is not a bounded operator. That is to say, there are sequences to which you apply the derivative, and it's not bounded. Instead, here, the shift operator is bounded. So you can give a sense to this, and you can even justify that you can do mathematical manipulations, sometimes even expansions. You can expand this in a series. Later, we will be exploiting this when we study prediction in a few classes from now. Okay, so but for the moment, be aware that these two representations of the system are equivalent, but they are different because here I have a representation in time, and here I have a representation in the frequency domain, in the Z domain. Okay, now I can write the shift, the so-called impulse operator of the system in this way. And I can even define polynomials B of Q and A of Q, and Q is an operator, but I work this to get the transfer function, just replace Q by Z, that's correct. Now, you can also define the backward shift operator. So the backward shift operator is an operator that shifts back your sequence, okay, by 1 unit. So if you start with your difference equation written in a second standard form in delays, okay, and you write y of k minus n as q minus n applied to yk, you can write the difference equation in symbolic terms in this way, and also here. Now, there is a funny thing, because there is an extra term here, which is the delay, the pure delay. The difference between n and m appears here, you see, n minus m appears. So you have to put it here. If you want to have a polynomial here, starting at b0, you have to add this term. Otherwise, it's not correct. Remember that b0 multiplies u of k minus n minus m, and all of the terms in u are multiplied by shifted by n minus m, and so on. Okay, minus 1, minus 1, minus 2, etc., up to k minus n. So you have this extra term. Now, this is important because these things are ways of representing your system. When you use the forward shift operator, or when you write your transfer function in Z, all the information is here in B and A. But if you write your equation in the delay operator, you have to add the extra information that about the delay. So it's not enough to have this polynomial and this polynomial. You also have to add the delay. Okay, remember that. There is a relationship between both things, both representations. And this representation comes from that. For a general polynomial, I define the reciprocal polynomial of A of Q as A of Q filtered or delayed by n. So Q minus n AQ. Okay, and I put a star here to say a star of q minus n is the reciprocal polynomial of q minus n aq. Okay, so I can write the transfer function in backward shift as b star divided by a star. Okay, and this a and b are a star and b star are the reciprocal polynomials of this a and b that appear here. Okay, very confusing? Yes, it's very confusing. But we are going to explore this and give more examples and along the progress. So we have these two representations in forward shift and backwards, backward shift. One is better for stability, as I said, and the other is better for designing. This will appear. Okay. Okay, so we jump this exercise. I would suggest that you do the exercise on your own. And if you have difficulties, we can start next class by answer questions related to this slide 99. So questions about this stuff? No questions? Foram cilindrados com esta parte final, não foi? So read the slides attentively. Try to solve this exercise in slide 99. And next week, we will start by seeing what is the solution, and you can ask me questions about this, okay? Any further questions or comments? Okay, so we stop here. See you next week and have a good week time work. Bye-bye.
Thank you.
Thank
Bye.
you, Professor.
Thank you.
Bye.
Bye, Professor.
Thank you.